Today we will explore the technique of transmission electron microscopy or TEM. This powerful analytical technique allows us to visualize both the structure and composition of materials down to atomic detail, which has revolutionized many fields. However, using TEM also comes with important limitations. Samples must be extremely thin, material contrast can vary, and specimens need to be vacuum compatible and stable under the electron beam. Understanding both the capabilities and limitations of TEM is essential for making most of this tool. We can use this diagram to understand the different types of signals generated when a high-energy electron beam interacts with a sample. Recently, we looked at scanning electron microscopy, or SEM, where an electron beam with an energy of typically 1 to 30 kV is scanned over a sample. By detecting backscattered or secondary electrons, an image of the surface is formed. But as the name suggests, transmission electron microscopy suggests we now shift our focus to the electrons that are transmitted through the sample when a much higher energy beam, typically 100 to 300 kV, is used. By detecting the electrons that have passed through the sample, the internal structure of materials can be imaged. Now, onto contrast modes. The most basic and commonly used imaging mode is bright field or BF, where an area of the sample is illuminated by a wide electron beam, which is then focused through an aperture onto a camera. In bright field TEM, image contrast arises due to differences in sample thickness, material density, and crystallographic orientation. Thicker or denser regions scatter more electrons away from the direct beam, making those areas appear darker. On the left, with a lower density, fewer electrons are deflected by the sample, allowing more electrons to reach the detector, resulting in higher intensity. Conversely, on the right, where the thickness is higher, more electrons are deflected and absorbed by the aperture. Consequently, fewer electrons reach the detector, creating a contrast between the areas. It is important to note that the scattering behavior remains consistent whether you have a sample of a certain density or another sample with double the thickness but half the density. In crystalline samples, contrast can also result from diffraction effects. When the crystal lattice spacings are on the order of the electron wavelength, they can cause diffraction patterns, similar to what we see in X-ray diffraction or XRD. These patterns can be recorded and analyzed to study crystal structures in detail. Scanning transmission electron microscopy combines ideas from both SEM and TEM. Like in SEM, a focused electron beam scans across the sample pixel by pixel. But instead of placing the detector above the sample, STEM collects signals that have passed through the thin sample, just like in TEM. This makes STEM a powerful contrast mode in itself. You can detect diffracted electrons, and because of how scattering works, heavier elements appear brighter in certain detectors. One of the most commonly used contrast modes in STEM is high-angle annular dark field, because the intensity depends on atomic number and thickness. While the image may look similar to SEM at first glance, STEM goes much further. You can collect multiple signals at once. For example, high-angle annular dark field, bright field, and EDX, or energy dispersive X-ray spectroscopy, all from the same scanned area, giving you detailed chemical and structural information. Before diving into using the TEM, it is important to understand two key constraints of the technique: vacuum conditions and sample thickness. TEM operates in a high vacuum environment. Without it, electrons would scatter in the air and never reach the sample or the detector. At the same time, the sample itself must be extremely thin, typically around 10 to 100 nanometers. Sample preparation is therefore essential for successful TEM analysis. There are various ways to prepare samples for TEM, and each method affects the result. That's why understanding how the sample was prepared is essential to interpreting your images correctly. Let's start with support grids. Samples are usually placed on 3 mm wide grids made from materials like copper or gold. These grids have a carbon support film that holds your sample in place. If you want to tilt the sample, for example in tomography, a grid with fewer mesh lines is better. Common sample preparation techniques. Drop casting. For fine solids like nanoparticles, you can disperse the particles in a solvent, place it on the grid, and let it dry. It's simple but effective for small particles. For powders and larger solids, you can also crush them into a fine powder and dip the support grid to pick up some material. ultramicrotomy, ideal for polymers and biological samples. You embed the material in resin and slice it into ultra-thin sections with a diamond knife. These sections can be transferred to a grid for imaging. Ion beam milling or thinning. Here, a focused ion beam is used to cut a slice or gradually erode a sample to the right thickness. It's useful for hard-to-cut materials and for making cross-sections of specific microstructures. After depositing the sample on the grid, it is placed in a sample holder and inserted into the microscope via an airlock procedure to ensure the microscope remains under vacuum at all times. It is also possible to image materials in 3D using electron tomography. Since TEM produces only 2D images, constructing a 3D projection requires combining multiple 2D slices by tilting the sample. Advanced reconstruction algorithms are used to accurately combine the 2D slices into a 3D model. Cryo-TEM. For samples in water or liquid, Cryo-TEM lets us vitrify the water, turning it into non-crystalline ice. This preserves the sample's native structure without damage.
Here you can see how preparation is done. Liquid nitrogen is used to cool down ethane to liquid, as it provides better heat transfer properties. The grid is then placed on the holder and the sample is added. The machine is used for quick solidification, retaining the original structure. The sample is then kept at cryogenic temperatures and then inserted into the cryo-TEM.
In situ experiments, where reactions are observed as they happen inside the microscope. This can also be done with TEM using the right equipment. Here you can see a video of electrodeposition of copper particles on an electrode using this method. Throughout all these methods, one thing to watch out for is artifacts, unintended features introduced during preparation. These could come from the solvent, slicing, grid, or even beam damage. Always ask yourself, is this structure real or is it an artifact?
Let's now take a look at how operating the microscope looks like. We can see here a fluorescent screen, which allows for the quick visualization of TEM results. You can see the sample grid here initially. The machine is operated using a joystick and buttons, and the screen allows for quick visualization. We can see the diffraction pattern here and then the sample itself. The screen can also be opened to display the image on the computer. Here we can see a bright field image of a gold and silver nanoparticle with a silica film.
In STEM mode, we can see both bright and dark field images simultaneously, which can give information about different parts of the sample.
If we zoom a bit out, more particles can be seen.
EDX, or energy dispersive X-ray spectroscopy, lets us identify which elements are present in a sample. When the electron beam hits the sample, it generates X-rays with element-specific energies. By detecting these, we can create elemental maps or analyze local composition, a valuable addition to the structural information of TEM.
As it can be seen, we can see a gold core, a silver shell, and a silica film all around it.
Accessing the facility. If you're interested in using TEM, our facilities are available for all users in principle.
To get started, send an email with your request to cmem@tui.nl and we'll send you an intake form to be filled in. Thank you for watching.